The James Webb Space Telescope recently found something that does not fit neatly into our best models of how the universe works. It found galaxies that look far too old, far too developed, and far too massive for how early they appear in cosmic history. And the more Webb looks, the more of these galaxies it finds. This is not a story about the Big Bang being wrong, it is a story about something more interesting. What happens when a theory you trust runs into data you did not expect? And what the possible explanations reveal about processes in the early universe that we clearly do not fully understand yet. If you're someone who enjoys going deeper than most people, who likes understanding things instead of just watching them, then you're exactly the kind of person I make these videos for. Subscribe and be part of this from the start. Let us start with the basic setup, because it is actually quite elegant. Telescopes are time machines. Light travels at roughly 300,000 kilometers per second, which sounds fast until you consider that the nearest star beyond our Sun is about 4 light years away. That means the light from that star takes 4 years to reach us. When you look at it tonight, you are seeing it as it was 4 years ago. For distant galaxies, that delay stretches into billions of years. The James Webb Space Telescope was specifically engineered to exploit this fact. It is the largest telescope ever deployed in space, with a primary mirror spanning 6.5 meters. And it is sensitive to infrared light, which is the stretched, reddened form that ancient light takes after traveling billions of light years through an expanding universe. Webb can look back to a time when the universe was only a few 100 million years old. That is roughly 2% of its current age of about 13.8 billion years. And what Webb was expected to find at those early times was a universe still in its infancy. Young, chaotic galaxies, small, irregularly shaped structures, furious but unorganized bursts of star formation. This is what the theory predicted, and it was a very well-supported prediction. What Webb actually found includes something much harder to explain. To appreciate why this matters, you need to understand a bit about how galaxies are supposed to form. The story begins before any stars existed, in the first fraction of a second after the Big Bang, when the universe was an almost perfectly uniform soup of matter and radiation. Almost perfectly uniform, but not quite. There were tiny fluctuations in density, regions where matter was ever so slightly more concentrated than elsewhere. We can actually see the imprint of those fluctuations. They show up in the cosmic microwave background, which is the faint thermal glow left over from when the universe cooled enough for atoms to form, roughly 380,000 years after the Big Bang. That glow is uniform to about 1 part in 100,000, but those small differences in temperature represent small differences in density. And those density differences were the seeds of everything that came after. Over billions of years, gravity amplified those small differences. Denser regions attracted surrounding matter and grew denser still. The most important component in this process was dark matter, a form of matter that does not interact with light and whose exact nature remains unknown, but which outweighs ordinary visible matter by a factor of roughly 5 to 1. Dark matter clumped first, forming enormous invisible structures called halos. These halos then pulled ordinary hydrogen gas in with them, and in the compressed, dense cores of those gas clouds, the first stars began to ignite. The first galaxies were built inside these dark matter halos. They were small at first, but because there was an enormous abundance of hydrogen gas in the early universe, they formed stars at a frantic rate. Over time, these small galaxies collided and merged, gradually building themselves up into the massive, complex structures we see nearby today. This model of galaxy formation is not a guess or a rough sketch. It is the product of decades of observations, refined measurements, and increasingly sophisticated computer simulations. The simulations incorporate what we know about gravity, gas dynamics, star formation, and the evolution of stellar populations. And one of the most confident predictions of the entire framework is this. In the very early universe, the dark matter halos should be small. Large halos take time to build up, through many mergers and the slow accumulation of matter. In the first 10% of the universe's age, which is roughly the first 1.4 billion years, there should not be many massive galaxies at all. That is what the theory says, that is what the simulations show, and that is what earlier, less powerful telescopes had seemed to confirm. But as telescopes got bigger and cameras got more sensitive, astronomers began to probe these early times with increasing precision. And about 15 or 16 years ago, something unexpected began to emerge. Early surveys of distant galaxies, which astronomers call high redshift surveys because the light from distant galaxies is stretched to longer, redder wavelengths by cosmic expansion, began turning up anomalies. A handful of galaxies that appeared too large and too evolved for how early they were. These were not dramatic discoveries at first. Just a few edge cases, a few outliers, things that did not quite fit but could perhaps be explained by observational errors or incomplete models. The redness was particularly puzzling. A galaxy that is actively forming lots of new stars should be bright at short, blue wavelengths, because newly formed massive stars are extremely hot and shine intensely at those wavelengths. A galaxy that stopped forming stars long ago will look much redder because the short-lived massive blue stars have already exhausted their fuel and exploded, leaving behind the longer-lived, cooler, redder lower mass stars. Finding red, evolved-looking galaxies at very early times implies that those galaxies had already finished most of their star formation, which implies they had started forming stars very early, grown rapidly, and then shut down, all before the universe had barely gotten started. In 2018, Charles Steinhardt and his team put a formal name to this emerging problem. They called it the impossibly early galaxy problem. That is a striking name, and it was chosen deliberately. Impossible is a strong word in science, but the observations at that time were pushing against the predictions hard enough to justify it. Still, impossible things require extraordinary evidence, and the observations from ground-based telescopes, while suggestive, were not airtight. There were enough potential sources of error that the most cautious response was to wait for better data. That better data came with the James Webb Space Telescope. Webb launched in December of 2021 and began science operations in mid-2022. From almost immediately, it started turning up anomalous results in the early universe. And the anomalies were not subtle. Webb found galaxies at redshifts corresponding to when the universe was only a few 100 million years old that appeared to be massive, evolved, and in some cases already largely done with their star formation. The number and degree of these cases exceeded what most astronomers had anticipated, even given the earlier ground-based hints. The most extreme confirmed case as of recent surveys sits at a redshift of 7.3, placing it at roughly 5% of the universe's current age. That means this galaxy, which appears to have a stellar population characteristic of a system that has been building stars for a long time and then slowed down, existed when the universe was only about 700 million years old. It should not look the way it looks. According to our standard models, it has not had enough time to look that way. And Webb keeps finding more of them. Not just one or two, a statistically meaningful population. At this point, some people concluded that the Big Bang model must be wrong, that the universe must be older than we think, that something fundamental in our cosmology needs to be discarded. That conclusion is premature, and it is worth being clear about why. The age of the universe is not a single measurement hanging on a single thread. It is a conclusion supported by multiple completely independent lines of evidence that all converge on the same answer. The cosmic microwave background, which is measured with extraordinary precision, supports a universe about 13.8 billion years old. The expansion rate of the universe, measured through observations of distant supernovae, supports that same age. The ages of the oldest stars in the oldest globular clusters are consistent with a universe that old. The abundance of light elements like hydrogen, helium, and lithium, which were forged in the first few minutes after the Big Bang, matches the predictions of Big Bang nucleosynthesis with remarkable accuracy. To explain the anomalous early galaxies by making the universe much older, you would have to simultaneously explain why all of these independent lines of evidence agree with each other so well. Then we work backward to estimate how many stars there are, how much they weigh, and from that we infer the mass of the dark matter halo that contains them. This process requires assumptions. One of the most important is something called the initial mass function, or the IMF. When a cloud of gas collapses and stars form, not all the stars are the same size. Some are massive, hot, and bright but short-lived. Others are small, cool, and dim but survive for billions or even trillions of years. The initial mass function describes the statistical distribution of stellar masses produced in a burst of star formation. It tells you, roughly speaking, for every massive star that forms, how many medium stars and how many small stars form alongside it. The IMF that astronomers use as a default is calibrated on observations within our own Milky Way and nearby galaxies. It is a reasonable starting point, but there is no guarantee that the same distribution applied in the very early universe. And there are theoretical reasons to expect it might not. In the early universe, there were far fewer heavy elements available. Elements heavier than hydrogen and helium, which astronomers collectively call metals regardless of their actual chemical nature, are produced inside stars and dispersed when those stars die. The very first stars formed from essentially pure hydrogen and helium. This lack of heavy elements affects how gas clouds cool and fragment as they collapse. Cooler, more fragmented clouds tend to form lots of smaller stars. But without heavy elements to radiate heat efficiently, gas clouds in the early universe may not have fragmented as readily, instead producing more massive stars relative to smaller ones. This is called a top-heavy initial mass function. More massive stars relative to low-mass stars compared to what we see today. And this matters a great deal for our mass estimates. Massive stars are tremendously luminous. If the early galaxies were producing proportionally more massive stars than our current models assume, then those galaxies would appear far brighter than their actual stellar mass would predict. When we look at that brightness and use the standard IMF to infer stellar mass, we would overestimate the stellar mass, and from the stellar mass, we infer the dark matter halo mass, so we would overestimate the halo mass too. In other words, those galaxies might not actually be as massive as they look, they might just be unusually bright for their mass. This is the top-heavy IMF solution, and for a while it looked like it might be the key to resolving the tension. But then a new study arrived, and it pointed in a troubling direction. The study attempted to identify nearby galaxies that are likely to be the modern descendants of the early impossibly massive galaxies. The logic is straightforward. If those early galaxies existed and grew into something over the past 13 billion years, there should be nearby examples today that evolved from them. And because these nearby galaxies are so much closer, we can observe their stellar populations in much greater detail, including the faint, low-mass stars that are invisible in very distant objects. What this study found when it measured the IMF in those likely descendant galaxies was not a top-heavy distribution, it was a bottom-heavy one. There were more low-mass stars, the dim red dwarfs and similar types, relative to massive stars compared to our standard IMF. This is a problem. A bottom-heavy IMF means those galaxies have more of their mass locked up in faint, low-luminosity stars that we cannot directly observe. When we measure the light from those galaxies at early times, we see only the bright end of the stellar population. If the stellar population is bottom-heavy, then there is significantly more mass hidden in stars too dim to detect. Applying the standard IMF or even a top-heavy IMF to those galaxies would cause us to underestimate the total stellar mass. And an underestimate of stellar mass leads to an underestimate of halo mass. So, rather than solving the problem, this finding makes it worse. The impossibly early galaxies might be even more massive than we already thought they were. Several cautions apply here. The authors of this study themselves described those nearby galaxies as likely descendants, not confirmed descendants. We do not know with certainty that they evolved from the same population Webb is finding at high redshift. And in the 13 billion years between then and now, these galaxies may have undergone mergers, interactions, and other processes that could have altered their stellar populations in complicated ways. Additionally, a bottom-heavy IMF does not automatically rule out a distribution that is also somewhat top-heavy. It is theoretically possible to have an IMF with an excess of both very low-mass stars and very high-mass stars compared to a Milky Way-like distribution, with relatively fewer stars in the intermediate mass range. Such a distribution might still allow the observed brightness of the early galaxies to exceed what their actual mass would predict, even if the total mass is also higher than we assumed. The IMF situation is therefore genuinely unresolved. It is not clear which direction this correction goes, and the uncertainty itself is scientifically meaningful. The second major area of possible explanation concerns the redness of the early galaxies. We said that a galaxy that looks red at early times implies it has finished most of its star formation, which implies it had to grow rapidly and then stop. What could cause such rapid quenching of star formation in the early universe? The leading candidate is quasar feedback. A quasar is an extremely luminous active galactic nucleus powered by a supermassive black hole that is actively accreting enormous amounts of matter. As matter falls toward the black hole, it releases tremendous amounts of energy, far more than can be produced by even the most active stellar populations. Quasars can outshine entire galaxies by factors of hundreds or thousands. When a quasar is active in the center of a galaxy, it does not just shine brightly, it also drives powerful winds and jets of energetic particles outward into the surrounding galaxy. These winds can heat up the gas in the galaxy, raising its temperature until it cannot cool efficiently enough to collapse into stars. They can also physically expel gas from the galaxy altogether. The effect is to cut off the raw material for star formation. Without cold dense gas, star formation stops. This process is called quasar feedback or AGN feedback, where AGN stands for active galactic nucleus. It is not a speculative process. We observe it happening in the nearby universe. Quasar feedback is already part of standard galaxy formation models, included in simulations as a mechanism for shutting down star formation in massive galaxies. The question raised by the early JWST galaxies is not whether quasar feedback happens, but whether it was dramatically more efficient in the early universe than our models assumed. If the first supermassive black holes grew faster and became more energetic sooner than predicted, they could have shut down star formation in their host galaxies very rapidly, leaving behind the red, evolved-looking populations we observe. This connects to another genuine open problem in astrophysics: the seeding and growth of supermassive black holes. The supermassive black holes that power quasars are enormous, sometimes billions of times the mass of our Sunday. But they had to start somewhere, from some kind of seed, and then grow to their current sizes through accretion of matter and mergers with other black holes. In the standard picture, this growth takes time. Yet quasars, powered by billion solar mass black holes, have been found at redshifts corresponding to when the universe was only a few 100 million years old. This is already a known tension in astrophysics, independent of the galaxy formation problem. Webb has made this tension sharper by finding evidence that supermassive black holes may have grown even faster and been even more common in the very early universe than previously understood. So the galaxy problem and the black hole problem may be deeply connected. The rapid growth of supermassive black holes might be both the explanation for why some early galaxies look old, through quasar feedback quenching their star formation, and a problem in its own right that needs explaining. There is also the question of dust. When we observe distant galaxies, we are not seeing them through empty space. The galaxies themselves contain dust, fine solid particles mostly composed of carbon compounds and silicates, which can absorb and scatter light. Dust particularly absorbs short-wavelength blue light and re-radiates it as longer wavelength infrared emission. A galaxy that is very dusty can appear red not because it has an old stellar population, but because its young, blue stars are hidden behind screens of dust. This is a known complication in interpreting the colors of distant galaxies. Photometric analysis, which is estimating properties from the overall brightness measured in several wavelength bands without actually resolving individual spectral features, is particularly vulnerable to this ambiguity. A dusty young galaxy and a less dusty old galaxy can produce similar color signatures. Distinguishing between them requires spectroscopy, the measurement of detailed spectral features that reveal the presence and temperature of stellar populations more directly. Webb has spectroscopic capability, and some of the anomalous early galaxies have now been confirmed spectroscopically. These confirmations have generally supported the interpretation of evolved, reddened stellar populations rather than dust-reddened young ones. But the sample of spectroscopically confirmed cases is still limited, and as it grows, the picture may become clearer or more complicated. What is striking about this entire situation is that it is genuinely a case of observations outrunning theory. Webb was designed to test our models of early galaxy formation at extreme look-back times, and it has found that our models, as good as they are, need revision. The only question is, how much revision, and in which direction? Some researchers have proposed modifications to the fundamental cosmological model, not throwing out the Big Bang, but adjusting parameters that govern how structure grows. For example, some models explore whether dark energy, the mysterious component driving the accelerating expansion of the universe, might have had different properties in the early universe than it has today. If dark energy was temporarily weaker in the early universe, structure could have grown faster, producing more massive halos sooner. Others have explored the possibility that dark matter is not a single, simple component, but has properties that allowed it to clump more efficiently in the early universe. Models of what is called self-interacting dark matter or other exotic variants have been considered in this context. These are speculative modifications, and none of them have strong independent support yet. But the fact that they are being seriously considered reflects how unusual the observational situation is. There is also a more mundane but important possibility: selection effects. When you build a telescope and look at the sky, you do not see everything. You see everything bright enough to detect. In the very early universe, most galaxies may have been too small and too faint to show up in Webb surveys. The galaxies that do show up are necessarily the brightest, and brightness is correlated with mass and star formation rate. So the galaxies Webb detects are not a representative sample of all early galaxies. They are the extreme cases. This is called Malmquist bias, and it has been a concern in galaxy surveys for a century. The question is whether the impossibly early galaxies are truly impossible, or whether they are simply the extreme high end of a distribution that, when the full population is included with all the faint, undetectable members, is actually consistent with our models. Working out the true underlying distribution requires careful statistical analysis and modeling of the survey selection effects. This work is ongoing, and the results suggest that while some correction for selection bias is certainly necessary, the anomaly does not completely disappear once this correction is applied. There is also the issue of the cosmic star formation history. We have measurements of how rapidly stars were forming across the history of the universe, derived from many different surveys at many different wavelengths and distances. This cosmic star formation history shows that star formation peaked when the universe was about 3 billion years old and has been declining ever since. If the very early universe contained many more massive, rapidly star-forming galaxies than our models predict, this should leave some imprint on the cosmic star formation history. So far, the imprint is not obviously seen in the existing measurements, though the precision of those measurements at very early times is limited. This is one of the areas where future observations will be crucial. Webb itself will continue to survey the early universe, building up the statistical sample of early galaxies and measuring them with increasing spectroscopic precision. The Nancy Grace Roman Space Telescope, a wide-field infrared observatory currently under development, will be able to survey much larger areas of sky than Webb and identify rare extreme objects across larger volumes of the early universe. Ground-based facilities are also playing a role. Extremely large telescopes with mirrors spanning 20 to 39 meters are currently under construction in Chile and Hawaii. Their enormous collecting area and sensitivity will allow them to take spectroscopic measurements of faint, distant objects that are barely detectable even with Webb. And the theoretical and computational side is advancing rapidly as well. Galaxy formation simulations have become extraordinarily sophisticated, running on some of the largest supercomputers available. Teams around the world are updating their simulations to include more realistic treatments of star formation, supernova feedback, black hole growth and feedback, the role of magnetic fields, and the effects of radiation from the first stars on the surrounding gas. As these simulations improve, they will either find ways to reproduce the Webb observations within the standard framework, or identify which assumptions need to change. The initial mass function is one area where significant theoretical work is happening. Understanding how the IMF depends on the properties of the star-forming gas, particularly its temperature, metallicity, and turbulent state, is a problem that combines stellar physics, fluid dynamics, and radiative transfer in complicated ways. Numerical simulations of individual star-forming clouds are becoming detailed enough to make predictions about how the IMF varies across different environments, and these predictions can eventually be tested against observations. Black hole seeding is another active research frontier. The earliest supermassive black holes could have formed through several different pathways. One possibility is that they are the remnants of the very first generation of stars, called population 3 stars, which were probably very massive by modern standards and collapsed directly into black holes at the ends of their brief lives. Another possibility involves the direct collapse of massive gas clouds into black holes without first passing through a conventional stellar phase. And a third involves the rapid merging of dense stellar clusters. Each of these scenarios makes different predictions about the mass distribution of early black holes and the timing of quasar activity, predictions that Webb observations can potentially distinguish between. The quasar feedback story is also gaining new observational texture from Webb. The telescope has already detected evidence for powerful outflows in several high redshift galaxies, massive flows of gas being driven out by active galactic nuclei. Characterizing these outflows, measuring their mass, velocity, and extent is exactly the kind of data needed to test whether quasar feedback was efficient enough to shut down star formation as rapidly as the observations of red, evolved early galaxies require. What is perhaps most intellectually significant about this situation is what it reveals about the scientific process itself. A theory as successful and comprehensive as our standard model of cosmology and galaxy formation is not going to be overturned by a surprising handful of observations, but it can be refined, improved, and extended in response to those observations. The impossible early galaxies are not evidence that we know nothing. They are evidence that we do not know everything, and that the edge of our knowledge is alive with unexplained phenomena. This is actually how major scientific advances tend to happen. Not through the discovery that everything we believed was wrong, but through the discovery that something we thought we understood was incomplete in some specific and revealing way. The discovery forces us to look more carefully, to measure more precisely, to simulate more realistically, and in doing so we often learn something fundamental and surprising about how nature works. The early galaxy problem is very likely to be resolved not by abandoning our model of the universe, but by discovering that galaxy formation in the early universe involved processes we had not fully accounted for. Perhaps a top-heavy initial mass function that made early galaxies brighter for their mass. Perhaps exceptionally rapid black hole growth driving powerful quasar feedback. Perhaps both together. Perhaps something else we have not yet clearly articulated. When we figure it out, the answer will not make the early universe more boring or more ordinary. It will make it more surprising, more detailed, and more vivid than we knew. The galaxies that seemed impossible will turn out to have been telling us something true about processes that operated when the universe was young, processes that have left their signatures in everything around us today. The James Webb Space Telescope was built to look at the edge of the observable universe, and it has done exactly that. What it found there was not confirmation of our expectations. It found a puzzle. And puzzles, in science, are how progress begins. What we know so far points clearly in one direction. The early universe was more active, more complex, and more extreme than our baseline models predicted. The galaxies at high redshift grew faster, became more massive sooner, and shut down their star formation more abruptly than the standard picture would suggest. These are not small discrepancies that can be waved away with minor tweaks. They represent a real and unresolved scientific tension. At the same time, the basic framework of modern cosmology remains robust. The universe is approximately 13.8 billion years old. It began in a hot, dense state, expanded and cooled, formed the first atoms, then stars, then galaxies, through the gravitational amplification of tiny primordial density fluctuations. All of this is supported by overwhelming evidence from multiple independent directions. The early galaxy problem is a problem within this framework, not a refutation of it. The next few years will be scientifically intense. Webb will continue building its catalogue of early galaxies. Spectroscopic surveys will constrain the physical properties of more of these objects with increasing precision. Theorists will update their models in response to what the observations reveal, and gradually the picture will sharpen. One thing seems increasingly clear. The universe in its earliest chapters was not a slow, quiet place waiting patiently for galaxies to assemble themselves over billions of years. It was vigorous, fast, and extreme. The physical processes that drove galaxy formation in those first few 100 million years operated at a pace and intensity that our models, calibrated on the gentler universe we see nearby, had not fully captured. Understanding exactly what those processes were and why they were so extreme is one of the most important open questions in contemporary astrophysics. The tools to answer it are in orbit, under construction, and running on supercomputers around the world. The impossible early galaxies, it turns out, are not impossible at all. They are just telling us something we did not yet know how to hear. And science, at its best, is the discipline of learning to listen more carefully. If you found this exploration of early cosmic structure worthwhile, consider sharing it with someone who would appreciate it. The questions at the frontier of cosmology deserve wider attention, and the answers, when they come, will be genuinely remarkable. Researchers are actively working to understand whether the initial mass function in the early universe truly differs from what we observe locally, and if so, by how much and in what direction. They are investigating the rapid growth of supermassive black holes and whether quasar feedback can operate powerfully enough, early enough, to produce the observed populations of quenched early galaxies. They are building more detailed simulations, designing new observing programs, and analyzing data from Webb that continues to accumulate. The early galaxy conundrum remains open. It has not been solved, and it has not gone away. What it has done is sharpen our understanding of what we do not yet know, and that is exactly where the most interesting science lives. Whether the resolution comes from a modified initial mass function, from more extreme quasar feedback, from subtle changes in our cosmological model, or from something not yet clearly on the table, the final answer will tell us something deep and true about the physics of the universe in its earliest and most extreme moments. And that is a genuinely exciting prospect. To truly appreciate the scale of what Webb is confronting, it helps to think carefully about timelines. The universe is 13.8 billion years old. Human civilization is roughly 10,000 years old. The earliest writing is about 5,000 years old. From the perspective of cosmic time, our entire recorded history is less than a blink. Now go back to when the universe was only 700 million years old. That is 5% of its current age. At that moment, the observable universe was smaller, denser, and bathed in a far more intense radiation field. The cosmic microwave background radiation, which today is chilled to just 2.7 degrees above absolute zero, was then hundreds of times hotter and more energetic. The large-scale structure of the universe, the cosmic web of filaments, sheets, and voids that today spans hundreds of millions of light years, was only beginning to emerge from those tiny primordial fluctuations. In that environment, our standard models say that the dark matter halos hosting galaxies should be relatively modest in size. The most massive halos should contain perhaps 10 to the 12 solar masses of dark matter, which is roughly comparable to a Milky Way-sized halo today. A truly massive halo, 10 times or 100 times more massive than that, should not exist yet. There simply has not been enough time for gravity to pull that much matter together. This prediction is one of the clearest and most testable outputs of our models. It does not depend heavily on the complicated physics of gas and stars. Dark matter is governed almost entirely by gravity, which we understand well. So, when dark matter halo mass predictions disagree with observations, it is particularly troubling because dark matter physics should be simpler and cleaner than baryonic physics, the physics of the ordinary matter that makes up stars and gas. And yet, the early galaxies Webb is finding appear to live in halos that are far more massive than predictions allow, at least based on how bright they are. Now let us think about the light travel time more carefully. When Webb detects a galaxy at a redshift of 7.3, the light from that galaxy has been traveling for roughly 13.1 billion years. The galaxy is not where it appears to be. Because the universe has been expanding throughout the journey of that light, the galaxy is now far more distant than 13.1 billion light years. In fact, due to the expansion, the galaxy's current location is roughly 28 billion light years from us, even though the universe is only 13.8 billion years old. This is one of the counterintuitive aspects of cosmology that trips people up. The observable universe is not a sphere 13.8 billion light years in radius. It is a sphere about 46 billion light years in radius, because the space we see was in the past much smaller than its current extent, and the expansion of that space has carried what we see much farther away than simple light travel time arithmetic would suggest. When we see a galaxy at 13.1 billion light years look-back time, we are seeing that galaxy as it was 13.1 billion years ago when it was much closer to us than it is now. At that time, the universe was much denser and more compact. Everything was closer together. The formation of structure was more rapid because the density of matter was higher and the gravitational interactions were stronger. That physical context is important for understanding star formation in the early universe. Higher matter density means more gas available per unit volume. More gas means more raw material for forming stars. And denser environments mean more frequent galaxy mergers, which are known to trigger intense bursts of star formation. So the early universe was inherently a more productive environment for star formation than today, and this is something the models already account for. The issue is not that the early universe was forming stars. The issue is that the most extreme early galaxies seem to have formed stars even faster than the models predict, and then stopped forming stars earlier than expected, and apparently already had this history completed by the time the universe was only a few 100 million years old. Understanding this requires thinking about what it means to stop forming stars. In a galaxy today, star formation happens in cold, dense molecular clouds of gas. These clouds form when gas in the galaxy cools and becomes gravitationally unstable. The gas needs to cool, which happens through radiation of energy, and it needs to be dense enough to overcome its own thermal pressure and collapse. Several processes can disrupt this cycle. Supernova, explosions from massive dying stars, inject energy into the gas, heating it and driving turbulence that prevents collapse. This is called supernova feedback, and it is an important regulatory mechanism in star formation. Without it, galaxies would have converted all their gas into stars very early, which clearly did not happen for most galaxies. But supernova feedback alone is not efficient enough to completely quench star formation in a massive galaxy. The deeper quenching mechanism, the one that shuts down star formation entirely in massive systems, appears to be quasar feedback. Here is how it works in more detail. A supermassive black hole at the center of a galaxy grows by accreting nearby gas. As gas falls toward the black hole, it spirals inward through an accretion disk, and as it does, gravitational energy is released as radiation. A small fraction of the infalling mass is converted to energy through this process, about 10% by mass in the most efficient cases. This is enormously more efficient than nuclear fusion, which converts less than 1% of hydrogen mass into energy. When the accretion rate is very high, the resulting radiation is intense enough to create a quasar, one of the most luminous persistent phenomena in the universe. The most luminous quasars outshine their entire host galaxies by factors of hundreds, and they drive winds, currents of energetic particles and radiation that push outward into the surrounding galaxy at speeds that can reach a significant fraction of the speed of light. These winds interact with the gas in the galaxy. They heat it, compress it, and in many cases drive it out of the galaxy altogether. Gas that has been heated to high temperatures cannot cool efficiently and collapse into molecular clouds, so star formation stops. Gas that has been physically expelled from the galaxy is gone entirely, unable to rein back in and fuel further star formation, at least not immediately. This is the quenching mechanism. And for galaxies that host very rapidly growing supermassive black holes, which is exactly what the most massive, luminous early quasars must have been doing, the quenching can be very rapid and very thorough. The challenge is that for this to explain the early Webb galaxies, the quenching had to be extraordinarily fast. In some cases, these galaxies appear to have completed most of their star formation within the first few 100 million years after the Big Bang. That requires both a period of extremely intense star formation and a period of very rapid and complete quenching, all compressed into a cosmically brief window. Achieving this with standard quasar feedback models is difficult. The black holes need to grow to very large masses very quickly, which is itself a problem, and the feedback needs to be more efficient at those early times than at later ones. Some theorists have proposed that the physics of feedback was indeed different in the early universe. Lower metallicity, which means less heavy element enrichment, affects how radiation couples to gas and dust. In a low metallicity environment, radiation from the quasar may couple differently to the surrounding gas, potentially making feedback more or less efficient depending on the specifics. Understanding exactly how this works requires detailed modeling of radiation-gas interactions in conditions quite different from what we can directly observe locally. This is one of the areas where the feedback between observations and theory is most productive. Webb is measuring the properties of real galaxies at high redshift, providing benchmarks that simulations must match. The simulations, in response, are identifying which physical parameters matter most and making predictions that can be tested with further observations. One particularly important observational probe is the measurement of gas outflow rates in early galaxies. When quasar feedback is operating, it should drive measurable amounts of gas out of the galaxy at high velocities. Webb is capable of detecting these outflows spectroscopically through the broadening and shifting of spectral lines from ionized gas. Early results have already revealed outflows in some high redshift galaxies, and characterizing these outflows statistically across the early galaxy population is a major ongoing science goal. The masses of gas being expelled, the velocities of the outflows, and the fraction of the galaxy's gas supply being removed in each episode of quasar activity, all of these constrain the efficiency of feedback and allow theorists to calibrate their models. We should also take a moment to consider what these early galaxies look like structurally. Modern large galaxies come in two main morphological types. Spiral galaxies like the Milky Way have a rotating disk of stars and gas, often with a central bulge and a bar, with spiral arms tracing regions of active star formation. Elliptical galaxies are more spheroidal in shape, with little organized rotation and very little ongoing star formation, typically old, red, and massive. The early evolved-looking galaxies Webb is finding at high redshift appear to be compact and already largely spheroidal in structure. They do not have the extended disk morphology we associate with actively star-forming systems. This is consistent with the interpretation that they have already assembled most of their stellar mass and ceased forming stars. but it also raises structural questions. How did they become so compact? Why are they spheroidal rather than disc-shaped? In the standard picture, very compact, dense stellar systems can form through extremely rapid, concentrated bursts of star formation, particularly in systems where large amounts of gas are funneled to the center through galaxy mergers or through instabilities in a gas-rich disk. This kind of formation pathway, sometimes called a dissipational collapse or a gas-rich merger, can produce compact, dense stellar systems quite naturally. But the compactness of the early JWST galaxies is extreme. They are significantly more compact than elliptical galaxies of similar mass in the nearby universe, which is itself a known and somewhat puzzling trend. Nearby massive ellipticals appear to have grown through dry mergers of already gas-depleted systems, which puff up their size without adding much new star formation. The early compact ellipticals must be the progenitors of today's large ellipticals, but the mechanism by which they grew in size over billions of years is still being worked out. This connects the high redshift galaxy problem to another active research area, the size growth of massive galaxies. Both phenomena point toward a picture in which the assembly of the largest galaxies was a multi-stage process, with the first stage involving rapid and intense star formation and early compaction, and subsequent stages involving growth through mergers that added stars at larger radii without much central star formation. Webb is in a unique position to probe both stages. By observing the early compact systems at high redshift, it provides a starting point. By tracing how galaxy populations evolve across cosmic time, from redshift 7 down through redshift 3, and then to redshift 1 and below, it can sketch out the growth history in greater detail than was previously possible. Understanding this growth history is not merely an academic exercise. The mass assembly history of galaxies is connected to the chemical enrichment of the universe, since stars produce the heavy elements and distribute them through stellar winds and supernova explosions. It is connected to the growth of the cosmic web, since galaxies trace the underlying dark matter structure. And it is connected to the thermodynamic history of intergalactic gas, since feedback from galaxies heats and redistributes gas across enormous scales. In short, the story of how galaxies form and evolve is deeply intertwined with the story of how the universe as a whole developed from the Big Bang to the present. The impossible early galaxies are a sharp point in a much larger picture, and pulling on that point reveals threads that run through many different areas of astrophysics. Let us also think about what the cosmic microwave background tells us more specifically. The CMB is our most precise snapshot of the very early universe, taken when it was only 380,000 years old. The temperature fluctuations in the CMB encode the density fluctuations that eventually grew into all the structure we see today. The amplitude of these fluctuations is characterized by a quantity called sigma-8, which measures the overall level of clustering on scales of 8 megaparsecs, roughly 26 million light-years. The value of sigma-8 inferred from the CMB, combined with our model of how structure grows over time, makes specific predictions for how much clustering we should observe in the galaxy distribution at different epochs. There is some current tension between the value of sigma-8 inferred from the CMB and the value inferred from some more direct measurements of clustering in the galaxy distribution. This tension is independent of the early galaxy problem, but may be related to it, since both could potentially point towards structure growing faster than the standard model predicts. Another important quantity is the Hubble constant, the current rate of expansion of the universe. There is a well-known and unresolved tension between the value of the Hubble constant measured from the CMB, which gives about 67 kilometers per second per megaparsec, and the value measured through observations of relatively nearby objects using the cosmic distance ladder, which gives about 73 kilometers per second per megaparsec. This is the Hubble tension, and it has been discussed extensively. A higher Hubble constant means the universe is expanding faster than the CMB measurement suggests. One consequence of a higher Hubble constant would be that the universe is somewhat younger, not older, than 13.8 billion years, since a faster expansion rate means everything was more compressed less time ago. This would, if anything, make the early galaxy problem worse, not better, since a younger universe means even less time for those early galaxies to have formed. Some proposals to resolve the Hubble tension involve modifications to the physics of the early universe, such as the existence of a brief period of extra dark energy in the first few 100,000 years. These modifications can change the sound horizon, a characteristic scale imprinted in the CMB, and the distribution of galaxies, in ways that affect the inferred Hubble constant. Some of these models have been explored in the context of the early galaxy problem as well, though no single modification has been found that solves both tensions simultaneously while remaining consistent with all other observations. This illustrates a broader point about modern cosmology. The standard model of cosmology, sometimes called lambda CDM, for its inclusion of a cosmological constant lambda representing dark energy and cold dark matter CDM, is remarkably successful. It accounts for an enormous range of observations with just a handful of free parameters. But the combination of the Hubble tension, the sigma 8 tension, and now the early galaxy problem suggests that there may be something subtle missing from the picture. Identifying exactly what is missing is one of the central intellectual challenges in cosmology today. The approach of modifying one thing and testing whether it helps more than it hurts, while remaining consistent with all other observations, is exactly the method scientists are applying. It is painstaking, it requires precise measurements and careful modeling, and it rarely produces instant answers. But it is how science at this level of sophistication advances. There is also something philosophically interesting about this moment in the history of cosmology. We have reached a level of observational precision where the uncertainties are no longer dominated by a lack of data. We have very good data from the CMB, from supernova surveys, from galaxy surveys, from gravitational lensing maps. The uncertainties that remain are increasingly in the realm of systematic effects, subtle biases in how we interpret what we measure, and in the modeling assumptions we bring to the data. This is both exciting and humbling. Exciting because it means we are genuinely at the frontier of what precision observations can tell us. Humbling because systematic uncertainties are often much harder to identify and control than random statistical uncertainties. An incorrect assumption about the stellar initial mass function, or an incomplete model of dust in distant galaxies, or a mischaracterized selection function in a survey can produce apparent discrepancies that are not real, or it can hide real discrepancies by compensating for them in unexpected ways. Distinguishing between these possibilities requires not just more data, but more diverse data. Observations at different wavelengths, using different techniques, probing different physical processes, are much less likely to share the same systematic biases than observations that use similar methods. This is why the community invests in a wide variety of observational approaches and facilities, rather than simply building one very powerful telescope and relying on it for everything. Webb is extraordinary, but it is not the only tool in the box. Radio telescopes, including current facilities and future ones like the Square Kilometre Array, probe cold gas and molecular content, which is directly related to the fuel for star formation. X-ray observatories detect the hot gas in galaxy clusters and the emission from active supermassive black holes, providing complementary information about energetic processes. Gravitational wave detectors, which have opened an entirely new observational window on the universe in recent years, are sensitive to merging compact objects and will eventually detect the gravitational wave background from supermassive black hole mergers across cosmic history. Taken together, these diverse observational tools are producing a richer and more complete picture of cosmic history than any single facility could provide. The early galaxy problem will ultimately be solved by bringing all of these strands together, and in doing so, it will illuminate not just the formation of early galaxies, but the fundamental physical processes that shape the universe we live in. It is worth ending on a note of appropriate perspective. The impossibly early galaxies are a puzzle, but they are a puzzle within a framework that has been tested more rigorously than almost any other scientific framework in history. The Big Bang model is not in danger of being overthrown. The fundamental picture of an expanding universe, of structure growing from primordial fluctuations, of stars and galaxies assembling over cosmic time, is supported by evidence so overwhelming and so mutually consistent that it is not going to be replaced. What is open to revision, and what the early galaxy problem is actively forcing scientists to reconsider, is the detailed picture of how galaxies form in the early universe. The initial conditions are not in question. The final products, the galaxies, clusters, and filaments we observe today are not in question. What is being refined is the path from beginning to present, and particularly the details of what happened in the earliest and most extreme phase of structure formation. This is how good science works, not by starting over, but by improving. The map is not thrown away, it is corrected, extended, and made more detailed, with each new measurement adding precision and each new anomaly pointing towards something previously overlooked. The galaxies Webb is finding are a genuinely remarkable scientific discovery. They are not scary, they are not universe-shattering. They are exactly what anomalies in good science are supposed to be: opportunities to learn something new and specific about how the world works. And in astrophysics, that opportunity is more accessible now than it has ever been. The tools are more powerful, the theoretical frameworks are more developed, and the scientific community's ability to integrate observations and models is more sophisticated. The early galaxy conundrum will be resolved, probably within the next decade, and when it is, the resolution will almost certainly teach us something fundamental and lasting about the physics of the early universe. That is worth paying attention to, that is worth being curious about. And that is why, even in a field as vast and abstract as cosmology, the discovery of a handful of galaxies that seem too old for their time has captured the attention of scientists and curious minds around the world. The universe is not done surprising us, and we are, perhaps for the first time, equipped to truly understand what those surprises mean. To get a sense of just how much our observational capabilities have improved in a short time, consider the following. 20 years ago, we did not have confirmed spectroscopic redshifts for any galaxy at redshift greater than 6.5. That corresponds to a time when the universe was about 900 million years old, less than 7% of its current age. At that point, the very existence of galaxies in the first billion years was more theoretical than empirically established. Then, in 2015, astronomers confirmed a galaxy at redshift 7.7 using ground-based telescopes equipped with powerful spectrographs. That was a record at the time. In 2017, another galaxy was confirmed at redshift 8.7. In 2018, a galaxy at redshift 9 was confirmed, placing it at a time when the universe was only about 500 million years old. Webb has shattered all of these records. Within its first year of operations, it confirmed galaxies at redshifts of 10, 11, 12, and even higher. One of the most remarkable confirmed cases places a galaxy at a redshift of 13.2, corresponding to a look-back time of about 13.4 billion years, when the universe was only about 320 million years old. That is 2.3% of the universe's current age. At that redshift, light has been traveling to us for longer than the Sun and Earth have existed. The photons we detect left that galaxy before our solar system had any material to work with. The atoms in your body had not yet been forged. The Milky Way itself was still in its very early assembly stages. And yet that galaxy, observed at this extraordinary look-back time, is already a substantial object. It has stars, it has structure, it has a history, however brief by cosmic standards. This is the observational reality that has forced theorists to take the early galaxy problem seriously. Not a handful of ambiguous photometric candidates, but confirmed, spectroscopically measured galaxies at extreme redshifts that have physical properties exceeding what our simulations predicted. One of the key tools Webb uses to confirm these galaxies and measure their redshifts is called the Lyman break technique, combined with spectroscopy. When a galaxy is at very high redshift, a specific feature in its spectrum, the Lyman break, gets shifted to longer wavelengths. The Lyman break is caused by neutral hydrogen in and around the galaxy, absorbing essentially all radiation at wavelengths shorter than about 122 nanometers in the rest frame of the galaxy. At very high redshifts, this break shifts from the ultraviolet into the visible and then into the near-infrared. Webb's infrared sensitivity means it can detect this break even at the most extreme redshifts. Photometric redshift estimates, which are based on the broad colors of the galaxy measured in several filter bands, and the identification of this Lyman break, can give approximate redshifts relatively quickly. But confirming a redshift precisely requires spectroscopy, the dispersal of light into its component wavelengths, and the identification of specific emission or absorption features at known wavelengths. Webb's near-infrared spectrograph, known as NIRSpec, can measure spectra of multiple galaxies simultaneously, making confirmation of photometric candidates much more efficient. The spectroscopic confirmations Webb has provided have been crucial for establishing that the early galaxy problem is real and not an artifact of photometric errors. In photometric surveys, the statistical uncertainties are larger, and there is a finite probability that a galaxy identified as being at very high redshift is actually a much closer interloper with unusual colors. Spectroscopy eliminates this ambiguity. There is also a class of objects that complicated early interpretations before spectroscopic confirmation became available. These are compact galaxies with very red colors that might have been interpreted as evolved, high redshift systems, but turned out to be something different on closer inspection. In particular, heavily dust-obscured star-forming galaxies can have very red photometric colors and can mimic the appearance of evolved high redshift galaxies in imaging surveys. Spectroscopy can distinguish between these possibilities by identifying the spectral features characteristic of active star formation, such as emission lines from ionized hydrogen, versus those characteristic of an old, quiescent stellar population, such as absorption features from cooler stellar atmospheres. Webb has produced a rich spectroscopic dataset in its first few years of operations. Not all of the early candidates have been confirmed as high redshift evolved systems. Some have turned out to be dust-obscured star formers at lower redshifts, but a significant subset has been confirmed as genuinely early, genuinely massive, and genuinely evolved. This confirmed subset is what makes the problem real. One of the powerful aspects of Webb's infrared sensitivity is that it can detect not just the direct starlight from these galaxies, but also the emission from warm dust in their interstellar medium. Dust emission appears at longer wavelengths than stellar emission, and in the very early universe, detecting this dust emission provides information about the chemical enrichment state of the galaxy. Dust is made of heavy elements, primarily carbon and silicates. The presence of significant amounts of dust in a very early galaxy implies that there have already been generations of stars that produced those heavy elements, lived out their lives, and dispersed their material through stellar winds and supernova explosions. In other words, dust is a proxy for stellar evolutionary history. Finding dusty galaxies at very early times is another way of discovering that those galaxies had already been forming stars for some time before we observed them, which puts further pressure on our timeline for galaxy assembly. Webb has detected dust in galaxies at remarkably early times. Some early epoch galaxies show evidence of substantial dust content even when the universe was only a few 100 million years old. This is consistent with the picture of rapid star formation and rapid chemical enrichment in the early universe, but it places stringent requirements on the rate at which the first stars must have formed and evolved. The relationship between dust content and galaxy mass at early times is also informative. At later epochs in the universe, the most massive galaxies tend to have the most dust because they have gone through more generations of star formation and produced more heavy elements. In the early universe, if the correlation between mass and dust holds, then very dusty early galaxies are likely to be very massive early galaxies, which again points toward rapid mass assembly in the first few 100 million years. Let us now consider what happens from the other direction, looking at the nearby universe for clues about early galaxy assembly. The galaxies we observe nearby today, including the large ellipticals that dominate the populations of massive galaxy clusters, appear to have formed most of their stars early in cosmic history and then stopped. This is inferred from their stellar populations, which are dominated by old, red stars, and from their chemical properties, which show high levels of enrichment consistent with early and intense star formation. Archaeologists studying ancient civilizations use what remains of past cultures to reconstruct history. Astronomers do something similar with nearby old galaxies. By measuring the ages and chemical properties of stars in nearby massive galaxies, we can, in principle, reconstruct when and how rapidly those stars formed. This is called galactic archaeology, and it is a powerful complement to direct observations of high redshift galaxies. Galactic archaeology studies of massive nearby ellipticals suggest that their stars formed predominantly at redshifts of 2 to 3 or even higher during a period of intense star formation that was over relatively quickly. The timescales inferred from this approach are in some cases uncomfortably short, suggesting star formation efficiencies that are difficult to reconcile with standard models. This is an independent line of evidence pointing in the same direction as the JWST observations, early and fast. The concordance between galactic archaeology and direct high redshift observation strengthens the case that the early galaxy problem is real. It is not just an artifact of how Webb observes things. It is a property of the universe that shows up in multiple ways. This convergence is how scientific problems gain confidence. When different methods of investigation, using different data and different assumptions, point toward the same conclusion, the probability that all of them are wrong in the same way becomes very small. The impossible early galaxies are telling a consistent story across multiple probes, and that consistency is what makes the story hard to dismiss. Now let us think about the theoretical landscape more carefully. The simulations that are used to model galaxy formation are extraordinarily sophisticated. They solve the equations of gravity, gas dynamics, and radiation simultaneously, tracking the behavior of matter across enormous ranges of scale, from individual star-forming regions a few light-years across to the large-scale cosmic web spanning hundreds of millions of light-years. These simulations, names like Illustris, Illustris TNG, Eagle, Simba, and more recently Fire and Flatiron Institute flares, have been remarkable successes. They reproduce many properties of the observed galaxy population across a wide range of cosmic epochs. The distribution of galaxy sizes, morphologies, colors, star formation rates, and chemical properties is broadly consistent with what these simulations predict. But the early JWST galaxies are straining these simulations. Several groups have run analyses asking whether the observed populations of massive, evolved early galaxies are consistent with what their simulations produce. The general finding is that while simulations can produce some examples of early massive galaxies, the observed number density, meaning how many of these objects exist per unit volume of the universe, often exceeds what simulations predict by factors of several to more than 10 in some mass and redshift bins. This overabundance relative to simulations is the core of the problem. It is not that simulations produce zero early massive galaxies. It is that observations find many more of them than simulations produce, and this suggests that whatever physical processes drive the rapid formation and evolution of these extreme systems are either not included in the simulations or are included but with parameters that are incorrect. Identifying which physical processes are misrepresented is the detective work that theorists are currently engaged in. The possibilities include star formation efficiency in the early universe being higher than standard assumptions, supernova feedback being less efficient at preventing star formation in the most massive early halos, black hole seeding happening earlier and more efficiently than current models assume, or cosmological initial conditions that produce somewhat more clustering at small scales than the standard model predicts. Each of these has been explored in modified simulations, and each produces some improvement. But so far, no single modification has been found to be both sufficient to explain the observations and consistent with all of the other constraints that simulations must satisfy. This is actually typical of how difficult problems in theoretical astrophysics get resolved. The solution is usually not a single change, but a combination of refinements, each individually small but collectively significant. And each refinement requires testing against not just the observations that motivated it, but the full range of observational benchmarks the simulation must match. One instructive parallel is the history of the missing satellites problem. In the 1990s, cosmological simulations predicted that the Milky Way should be surrounded by hundreds or even thousands of small satellite galaxies. Observations at the time found only a few dozen. This was called the missing satellites problem, and it was taken seriously as a potential challenge to the standard cosmological model. Over the subsequent decades, the problem was largely resolved, not by changing the cosmological model, but by improving the models of how baryons, ordinary matter, behave inside dark matter halos. Better models of supernova feedback, reionization effects, and the role of the cosmic ultraviolet background in photoionizing and heating gas showed that most small halos should contain very little visible matter or none at all. At the same time, increasingly sensitive surveys of the Milky Way's environment discovered more and more faint satellite galaxies. As predicted, the missing satellites are there. They are just very faint. This history suggests a path for the early galaxy problem. Not an overturning of the standard model, but a refinement of how baryonic physics operates within it. The trick is to find the specific physical mechanisms that make early galaxy formation more efficient and early quenching more rapid than current models predict, without breaking all of the other things those models get right. Researchers working on this problem are some of the most creative minds in theoretical astrophysics. The variety of proposed solutions, from top-heavy initial mass functions to rapid black hole seeding to modified dark matter models to exotic early dark energy, reflects both the seriousness of the problem and the openness of the field to diverse approaches. What is particularly interesting from a scientific philosophy standpoint is that the early galaxy problem is forcing cosmologists to confront the interface between the well-tested large-scale picture, where the standard model is extraordinarily robust, and the messier and more complex world of galaxy formation physics, where empirical uncertainties and modeling challenges remain significant. The cosmological model, describing the composition and expansion history of the universe, is tested on scales of hundreds of megaparsecs and above. On those scales, the universe is relatively simple, described by a few well-measured parameters. Galaxy formation, by contrast, happens on scales of kiloparsecs and below, where gas physics, stellar evolution, black hole accretion, and radiation all interact in complicated and non-linear ways. The early galaxy problem lives precisely at the intersection of these two regimes. The large-scale initial conditions are known, the final products are observed. The challenge is in the complicated middle. What happened in the transition from uniform gas to structured galaxies, particularly in the first billion years when the conditions were most extreme and the physical processes were operating most rapidly? This is why the early galaxy problem is so scientifically rich. It is not a single question with a single answer. It is a window into a complex and poorly understood regime of astrophysics, and every observation, every confirmed redshift, every measured spectrum adds another constraint on what the answer can be. Webb will continue operating for at least a decade, and possibly longer. During that time, it will build a statistically robust sample of early galaxies across a wide range of masses and redshifts. This sample will allow astronomers to trace the evolution of the galaxy population in the early universe with unprecedented detail, measuring how the abundance, size, structure, and stellar population properties of galaxies change from redshift 10 down to redshift 2. The Roman Space Telescope, if funded and launched as currently planned, will complement Webb with wide-field surveys covering much larger areas of sky. Where Webb goes deep but narrow, Roman will go wide, finding the rare, extreme objects that are too few in number to be well sampled in Webb's smaller fields. Together, these two observatories will provide a comprehensive view of galaxy evolution across cosmic time. Ground-based support will be essential as well. The Giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope will all provide spectroscopic capabilities for objects that Webb identifies but cannot fully characterize. The combination of space-based discovery and ground-based follow-up has been the model for many of the most productive observational programs in modern astronomy, and it will be the model for resolving the early galaxy problem as well. And as observations advance, so will theory. Simulations are becoming more powerful as computing hardware improves and algorithms become more efficient. Machine learning approaches are being applied to identify patterns in simulation outputs and observational data, helping to identify which physical parameters have the most influence on the properties of early galaxies. The combination of high-quality observations, sophisticated simulations, and advanced data analysis methods represents the state-of-the-art in modern astrophysics. It is a genuinely powerful combination, and there is good reason to be optimistic that the early galaxy problem will yield to this approach within the coming decade. When it does yield, the answer will be worth knowing. Understanding how galaxies formed in the earliest phases of the universe is not just an academic exercise, it is the foundation of our understanding of cosmic history. Every atom of carbon in every living thing on Earth was forged inside a star. The conditions under which those first stars formed and the galaxies in which they lived determine the chemical composition and large-scale structure of everything that came after, including us. The impossible early galaxies are a chapter in our own origin story. Understanding them is, in a very real sense, understanding where we came from. There is another dimension to the early galaxy story that deserves careful attention, and it involves the role of environment. Galaxies do not form in isolation. They form within the cosmic web, a vast network of filaments, sheets, walls, and voids that traces the distribution of dark matter across the universe. The denser nodes of this web, where multiple filaments intersect, are where galaxy clusters form. The filaments themselves channel gas and smaller galaxies toward these nodes, and the vast voids between filaments are largely empty, containing few galaxies and little gas. This environmental context matters for galaxy formation in ways that are still being actively investigated. Galaxies in dense environments near the nodes of the cosmic web are systematically different from galaxies in less dense environments. They tend to be more massive, more evolved, and more likely to have stopped forming stars. This is not a coincidence. Dense environments promote more frequent galaxy mergers, which can trigger bursts of star formation and also fuel black hole growth. Dense environments also mean more intense radiation fields and more energetic interactions with surrounding gas. At very early times, when the universe was only a few 100 million years old, the cosmic web was already beginning to emerge from the primordial fluctuations. The densest regions, the protoclusters that would eventually grow into today's massive galaxy clusters, were already experiencing enhanced galaxy formation activity. Some of the massive, evolved early galaxies Webb is finding may be preferentially located in these proto-cluster environments. This environmental connection could be part of the explanation for why some early galaxies appear so advanced. If they formed at the densest intersections of the early cosmic web, they had access to more gas, experienced more frequent mergers, and hosted more rapidly growing black holes. All of these factors would accelerate their evolution relative to galaxies in average environments. Identifying proto-cluster environments at high redshift is observationally challenging. It requires finding overdensities of galaxies in both angular position on the sky and in redshift space, and this requires surveying large areas with enough sensitivity to detect the faint galaxies that populate the outskirts of these overdensities. Webb, combined with wide-field ground-based survey, this would make them extreme objects in extreme environments, and it would change the statistical arguments about how common they are. Understanding the environmental dependence of early galaxy evolution requires a combination of imaging surveys to map galaxy positions across large areas and spectroscopic surveys to confirm redshifts and measure physical properties. The goal is to construct a three-dimensional map of the galaxy distribution in the early universe, analogous to what large redshift surveys have done for the nearby universe, but reaching back to the first billion years. This is an ambitious goal, and it will take many years and many observing programs to achieve fully, but Webb, Roman, and the next generation of ground-based observatories are collectively capable of making substantial progress toward it within the next decade. The cosmic web itself has something interesting to tell us in this context. The properties of the web, meaning the typical sizes of filaments, the characteristic distances between clusters, and the density contrasts between nodes and voids, are directly determined by the power spectrum of primordial density fluctuations and the parameters of the cosmological model. Measuring the statistical properties of the high redshift galaxy distribution provides an independent test of the cosmological model, separate from the CMB and from supernova measurements. If the early galaxy population is more clustered, more massive, and more evolved than the standard model predicts, this might reflect an underlying power spectrum with more power at small scales than the standard model assumes. In other words, the primordial fluctuations that seeded structure formation might have been slightly larger at the scales corresponding to galaxy formation than our standard model of inflation predicts. Inflation is the period of extremely rapid exponential expansion that the universe underwent in the first tiny fraction of a second after the Big Bang. It is the mechanism thought responsible for producing the nearly scale invariant spectrum of primordial fluctuations we see imprinted in the CMB. The standard inflationary model predicts a spectrum with a slight tilt toward more power at large scales, described by the spectral index, which has been measured to be about 0.96. If the early galaxy problem turns out to require more power at small scales, this could be a signal that the inflationary potential, the function that describes the energy of the field driving inflation, has a shape that produces slightly more small-scale fluctuations than the simplest models predict. This is not a wildly exotic idea. Many inflationary models have been proposed that produce exactly this kind of feature in the primordial power spectrum. The challenge is that the CMB measurements are so precise that they constrain the primordial spectrum very tightly on the large scales they probe. Any departure from a simple power law must be consistent with the CMB while also being large enough to affect galaxy formation at the small scales relevant to early galaxy masses. This is a genuinely interesting observational target. Measuring the clustering statistics of early galaxies with enough precision to constrain the primordial power spectrum at small scales would be a remarkable scientific achievement, providing information about the physics of inflation that is complementary to what CMB measurements provide. Let us take a step back and put the James Webb Space Telescope in historical context. Every era of observational astronomy has been defined by a new instrument or new technique that pushed the boundaries of what could be observed. Galileo's telescope revealed moons around Jupiter and phases of Venus, shattering the Ptolemaic model of a perfect, unchanging cosmos with Earth at the center. The introduction of photographic plates in the 19th century allowed astronomers to record faint objects that could not be seen by eye, enabling the systematic survey of nebulae that eventually led to the understanding that many of them were distant galaxies. Edwin Hubble's use of the 100-inch telescope at Mount Wilson in the 1920s allowed him to measure the distance to the Andromeda Nebula, establishing that it was a galaxy far beyond our own Milky Way. His subsequent measurements of the recession velocities of many galaxies established the expansion of the universe, one of the most transformative discoveries in the history of science. The introduction of radio astronomy after World War II opened a completely new window on the universe, revealing pulsars, quasars, the cosmic microwave background, and the large-scale structure of the cosmic web. X-ray astronomy, launched into the space age in the 1960s and 70 years, revealed a high-energy universe of neutron stars, black holes, and hot intracluster gas. Infrared astronomy uncovered dusty star-forming regions and the cool side of the universe, hidden from optical light. The Hubble Space Telescope, launched in 1990, brought optical astronomy to a new level of clarity by operating above Earth's turbulent atmosphere. Its deep-field images, exposures of tiny patches of sky taken over many days, revealed thousands of galaxies across the full range of cosmic history and became some of the most iconic images in science. Webb represents the next step in this tradition. It operates primarily in the infrared, at wavelengths from about 0.6 to 28 micrometers, which allows it to detect the light from very distant, redshifted objects that are invisible to optical telescopes. Its mirror is almost 3 times the diameter of Hubble's, giving it roughly 7 times more light-collecting area. And it operates far from Earth, at the second Lagrange point 1.5 million kilometers from Earth, where it is shielded from the sun's heat and can maintain the extremely cold temperatures needed for sensitive infrared observations. The planning, design, and construction of Webb took more than 25 years. The telescope was originally conceived in the 1990s as the successor to Hubble, and its development involved hundreds of scientists and engineers from multiple countries and space agencies. When it finally launched on Christmas Day of 2021 and began its commissioning process, the scientific community waited with a mixture of excitement and anxiety, knowing that both its capabilities and its discoveries would define the next generation of cosmology. The first science results, released in July of 2022, exceeded even optimistic expectations in terms of image quality and sensitivity. The deep fields revealed galaxies in exquisite detail. The spectroscopic capabilities exceeded performance requirements. And almost immediately, candidate high redshift galaxies began appearing that pushed the boundaries of what our models could explain. The story of Webb's early galaxy discoveries is therefore also a story about scientific anticipation, instrument design, and what happens when a revolutionary new tool encounters the universe for the first time. It is a reminder that progress in science often comes not from gradual accumulation, but from sudden expansions in capability that reveal what was previously hidden. And what was hidden, in this case, is a population of massive, evolved galaxies forming and maturing when the universe was barely underway. Their presence is a genuine surprise, consistent with everything else we know about the universe, but inconsistent with the specific predictions of our galaxy formation models. This is exactly the productive tension that drives science forward. It is also worth noting what Webb is not finding, or rather, what it has not found that would truly upend cosmology. It has not found galaxies at redshifts much higher than about 16, which would correspond to times before the first stars could plausibly have formed, given our understanding of the primordial universe. It has not found galaxies with metallicities or ages inconsistent with a universe that is roughly 13.8 billion years old. It has not found evidence for a cosmological constant that is dramatically different from our measured value. In all of these respects, the standard model remains intact. What Webb has found is that within the standard framework, galaxy formation in the first billion years was more vigorous, more efficient, and more extreme than predicted. This is not a crisis. It is an invitation to improve our models. The scientists working on this problem are genuinely excited. This is exactly the kind of challenge that motivates careers in astrophysics. Observations that push against the boundaries of understanding, that require theoretical creativity and observational precision to resolve, and that promise to deepen our knowledge in ways that cannot be fully anticipated in advance. The history of astrophysics is filled with apparent paradoxes that turned out to be opportunities. The ultraviolet catastrophe in classical physics, which predicted that a perfect radiating body should emit infinite energy at short wavelengths, seemed to contradict experiment but led directly to quantum mechanics. The observation that the universe's expansion is accelerating, discovered through supernova surveys in the 1990s, was deeply puzzling, but led to the framework of dark energy that is now central to the standard cosmological model. The observation that many galaxy rotation curves do not match the predictions of Newtonian gravity based on visible mass alone seemed to violate basic physics, but led to the concept of dark matter. In each case, An apparent contradiction between observation and theory did not mean that physics was broken. It meant that physics was incomplete. The resolution required new concepts, new frameworks, and new ways of thinking about how the universe works. And each resolution produced not just a patch for the specific problem, but a deeper and more powerful understanding of nature. The early galaxy problem is younger than these examples, and its resolution is not yet in sight. But there is every reason to expect that when it is resolved, the resolution will similarly deepen our understanding of the universe in ways that are currently difficult to anticipate. In the meantime, the data keep coming. Webb continues to observe. Spectra are measured, redshifts are confirmed, stellar populations are characterized, dust is detected, gas outflows are mapped. And with each new dataset, the contours of the problem become sharper and the range of viable solutions narrows. This is science as it is actually practiced, not a series of dramatic revelations, but a steady accumulation of evidence, interpreted in the context of improving theoretical models, guided by the interplay between what we observe and what we expect. The impossible early galaxies are part of this ongoing process, and their eventual explanation will be a genuine contribution to human knowledge. There is something deeply satisfying about the fact that we live in an era when these questions are even askable. For most of human history, the nature of the universe beyond our immediate surroundings was a matter of myth, religion, and philosophical speculation. The scientific revolution of the 16th and 17th centuries began the process of replacing speculation with measurement. And over the subsequent centuries, that process has produced an extraordinary body of knowledge about the universe we inhabit. We now know the age of the universe to better than 1% precision. We know its composition, the relative amounts of ordinary matter, dark matter, and dark energy to within a few percent. We know the detailed pattern of temperature fluctuations in the cosmic microwave background, the statistical distribution of galaxies across billions of light years, the distances to billions of individual stars and millions of galaxies. We have detected gravitational waves from merging black holes and neutron stars across the universe. We have imaged the shadows of supermassive black holes in 2 nearby galaxies. This is an extraordinary body of knowledge, and it is the foundation on which the current questions rest. The impossible early galaxies are not a challenge to this foundation. They are a challenge to the next level of the structure, the detailed model of how galaxies form and evolve within the well-established cosmological framework. Resolving this challenge will require the same combination of observational precision, theoretical creativity, and scientific rigor that produced the foundation in the first place. And there is no reason to doubt that the scientific community is up to the task. The universe began with an almost perfect simplicity, nearly uniform matter, cooling and expanding, governed by forces whose behavior we understand in exquisite detail. From that simple beginning emerged an almost incomprehensible complexity. Galaxies, stars, planets, chemistry, biology, consciousness. The process by which simplicity became complexity is the deepest question in science, and every part of that process that we manage to understand is a genuine achievement. The earliest galaxies are among the first steps in that process. Understanding them is understanding the beginning of the world as we know it. And that is a project worth pursuing with every tool at our disposal and every insight we can muster. The Webb telescope will not be the last word. It will be one chapter in an ongoing story of exploration. Future generations of astronomers will look back at this era as the time when we first glimpsed the earliest galaxies in real detail, when we first confirmed that galaxy formation in the early universe was more extreme than expected, and when we began the work of figuring out why. That work continues today, and it is, by any measure, among the most consequential scientific work being done. If you have found these ideas compelling, if the question of how galaxies formed in the very first chapter of cosmic history seems worth asking and worth answering, then you already understand why so many scientists have dedicated their careers to this field. The universe is very large and very old, and we are very small and very recent. But we are curious, and we are capable, and we are asking the right questions. That is enough. Consider for a moment the sheer audacity of what modern astrophysics attempts. We look at light that has been traveling for more than 13 billion years. We measure tiny wavelength shifts caused by the motion of galaxies relative to us. We infer the temperature, mass, chemical composition, and age of stellar populations from patterns in that light. And from all of this, we reconstruct the history of the universe from its very beginning to the present. This reconstruction is never finished. Every new observation adds detail, corrects errors, and in some cases reveals surprises that require us to revisit our assumptions. The early galaxy problem is one of those surprises, and it is a particularly rich one because it sits at the intersection of so many different threads: the physics of dark matter, the initial conditions from inflation, the complex baryonic processes of star formation and feedback, the growth of supermassive black holes, and the fundamental cosmological framework that ties everything together. One aspect of the problem that deserves more attention is the role of reionization. In the universe's first few 100 million years, after the cosmic microwave background was released and before the first stars formed, the universe was dark. There were no sources of light. The gas between nascent structures was neutral hydrogen, opaque to ultraviolet photons. This period is sometimes called the cosmic dark ages. When the first stars ignited, their ultraviolet radiation began to ionize the surrounding neutral hydrogen. This process, called reionization, gradually transformed the intergalactic medium from a neutral, opaque state to the ionized, transparent state it is in today. Reionization is not instantaneous. It is thought to have begun when the universe was a few 100 million years old and was largely complete by the time the universe was about 1 billion years old, corresponding to a redshift of about 6. The timing and character of reionization are directly connected to the early galaxy problem. The sources that drove reionization, primarily young massive stars in early galaxies, needed to be numerous enough and luminous enough to produce the ultraviolet photons required. Our estimates of how many such sources there were at different redshifts are derived from galaxy surveys, including Webb's observations of the very high redshift galaxy population. If there are more galaxies at early times than our models predict, this means there may have been more sources of reionizing photons. The history of reionization would then be slightly different from what the standard model predicts, potentially beginning earlier and proceeding faster. There are observations that can probe the reionization history. The spectra of distant quasars show absorption by neutral hydrogen along the line of sight, and the pattern of this absorption changes as the fraction of neutral hydrogen in the intergalactic medium evolves over time. At redshifts below about 6, the intergalactic medium is nearly completely ionized, and the spectra of quasars transmit freely. At higher redshifts, increasing amounts of neutral hydrogen absorb the light, eventually producing what is called the Gunn-Peterson trough, a complete blackout of the quasar spectrum at wavelengths shorter than the redshifted Lyman alpha emission line. The transition between these regimes, the epoch of reionization, is encoded in the statistical properties of quasar spectra at redshifts of 5 to 8. Webb and ground-based observatories are studying this transition in detail. If the early galaxy problem is connected to a higher than expected number of ionizing sources, this should leave a detectable signature in the reionization history. Conversely, the radiation environment during and after reionization has feedback effects on galaxy formation. When the intergalactic medium is reionized, it is also heated. This heating raises the temperature of intergalactic gas to tens of thousands of degrees, which is hot enough to prevent it from falling into small dark matter halos. Small halos, with masses below a certain threshold, cannot hold on to heated gas, and so they cannot form stars. This effect, called reionization feedback or photoionization suppression, is expected to reduce the number of faint galaxies at late times compared to what would exist without reionization. At early times, before or during reionization, this suppression is less effective because the ionizing radiation field has not yet built up to its full intensity. This means that the earliest, smallest galaxies may have been somewhat easier to form than their later counterparts. This is another factor that could contribute to a higher effective galaxy number density at early times. The interplay between reionization and galaxy formation is a complex two-way process. Galaxies drive reionization by producing ionizing photons. Reionization suppresses subsequent galaxy formation in small halos, and the timing and character of both processes are determined partly by the early galaxy population itself. Disentangling these effects requires carefully modeling the full coupled system, which is exactly what the most sophisticated current simulations attempt to do. One of the most technically challenging aspects of this problem is what is called the escape fraction of ionizing photons. Not all of the ultraviolet photons produced by massive stars in early galaxies escape into the intergalactic medium. Many are absorbed by the neutral hydrogen and dust within the galaxy itself. The fraction that escapes, the escape fraction, determines how many photons are available to drive reionization. Measuring the escape fraction in high redshift galaxies is extremely difficult. The ionizing photons themselves are absorbed by intervening neutral hydrogen before they reach us, so we cannot detect them directly. We have to infer the escape fraction indirectly, through a combination of observed properties like the compactness of the galaxy, the strength of certain emission lines, and the properties of the surrounding gas. Webb provides better constraints on these proxy measurements than any previous telescope, and improving our understanding of the escape fraction in early galaxies is a significant ongoing science goal. The relationship between the escape fraction and other galaxy properties is also scientifically interesting in its own right. Compact, low metallicity galaxies appear to have higher escape fractions. If the early massive galaxies that Webb is finding are typical in having compact morphologies and low metallicities, they might also have had high escape fractions, making them particularly efficient at driving reionization. This creates an interesting scenario. The same galaxies that are challenging our models of galaxy formation by being too massive and too evolved might also be the ones that are most responsible for reionizing the universe. Understanding them is therefore not just about galaxy formation in isolation, but about a fundamental phase transition in the history of the universe. Moving from the very early universe to slightly later times, there is a period around redshifts of 2 to 3, corresponding to when the universe was about 2 to 3 billion years old, that is sometimes called cosmic noon. This is when the overall star formation rate of the universe peaked. More stars were being formed per unit volume per unit time at cosmic noon than at any other epoch. The most massive, most actively star-forming galaxies at cosmic noon were producing stars at rates of thousands of solar masses per year, compared to just a few solar masses per year in the Milky Way today. These cosmic noon starburst galaxies are thought to be among the direct descendants of the early high redshift galaxies Webb is finding. The timeline goes something like this: early intense star formation and rapid mass assembly in the first billion years, as Webb is observing, followed by continued growth and merging activity, reaching peak star formation rates around cosmic noon, and then a gradual decline as gas is consumed, expelled by feedback, or heated to the point where it cannot form stars efficiently. This is the broad outline, but the details are poorly understood. What determines when a galaxy transitions from rapid star formation to quiescence? Why do some massive galaxies quench early, while others continue forming stars until cosmic noon or beyond? How does the quenching relate to black hole activity? And why is that relationship apparently so tight that there is a well-observed correlation between the mass of a galaxy's central black hole and the mass of its stellar bulge? The black hole to bulge mass correlation is one of the most tantalizing observations in galaxy science. It suggests that the growth of a galaxy's stars and the growth of its central black hole are closely connected, despite the fact that the black hole is millions of times smaller in physical size than the galaxy. How could something so small influence the properties of something so large? The answer, most scientists believe, lies in feedback. As the black hole grows and powers a quasar, its energy output is comparable to or greater than the gravitational binding energy of the galaxy's gas reservoir. Even if only a small fraction of the quasar's energy is deposited in the gas, it can have a dramatic effect on star formation, and the feedback mechanism is self-regulating. If too much gas falls into the black hole, the resulting quasar shines too brightly and expels the gas, cutting off the accretion and dimming the quasar. If too little gas falls in, the quasar is dim, feedback is weak, gas cools and falls toward the center, and the cycle repeats. This self-regulation could explain why the black hole and bulge masses are so closely correlated. The system naturally finds an equilibrium, and the parameters of that equilibrium determine the final black hole to bulge mass ratio. But whether this picture is actually correct in detail, and what determines the specific value of the correlation, are questions that remain active areas of research. In the context of the early galaxy problem, the black hole to bulge mass correlation is important because it suggests that in the most massive early galaxies, there should be very massive black holes, potentially growing through rapid accretion in the form of early quasars. If those early quasars were responsible for quenching star formation in their host galaxies, they must have been extremely energetic and reached very high masses very quickly. Webb has already discovered several candidate quasars at very high redshifts, including active black holes with masses of tens or even hundreds of millions of solar masses at times when the universe was only a few 100 million years old. These observations are consistent with, and in fact even more extreme than, the early galaxy problem would suggest for the typical object. They imply that the most massive black holes in today's universe seeded themselves and grew extremely rapidly in the first few 100 million years. How this rapid growth was achieved is a deep open question. In the standard picture, black holes grow primarily by accreting gas, and the rate of accretion is limited by a physical process called the Eddington limit. When a black hole is accreting at the Eddington rate, the radiation pressure from the infalling gas exactly balances the gravitational attraction. Accreting faster than this limit is possible, but requires specific conditions, and it may have been more feasible in the dense, gas-rich environments of the early universe. Even at the Eddington limit, growing a black hole from a few hundred solar masses, which is what the first stellar mass seed black holes would have been, to billions of solar masses in only a few 100 million years requires continuous, uninterrupted Eddington-limited accretion. This is difficult to achieve and maintain, and yet the observations suggest it happened. Alternative seeding mechanisms that produce much more massive initial black holes have therefore gained interest. Direct collapse black holes, formed from the collapse of massive gas clouds without first passing through ordinary star formation, could start with masses of 10,000 to 100,000 solar masses. From such a massive seed, reaching billions of solar masses in a few 100 million years is much more feasible, even without sustained Eddington-limited accretion. The detection and characterization of these early massive black holes by Webb and eventually by the Laser Interferometer Space Antenna, which will detect gravitational waves from merging supermassive black holes at cosmological distances, will be crucial for understanding how this rapid early growth occurred. All of these threads, early galaxy formation, black hole seeding and growth, quasar feedback, reionization, and the initial conditions from inflation, are woven together into a single coherent story about the first billion years of cosmic history. And the early galaxy problem is a tension in that story that is pointing towards something we do not yet fully understand. Science, at its most productive, is exactly this: a collection of observations that cannot all be simultaneously explained by the current best model, driving theorists to be more creative and observers to be more precise, until a new and better understanding emerges. The Galaxies Webb has found at the edge of the observable universe galaxies that seem to have grown up too fast in a universe that was too young to have given them that much time, are doing exactly this. They are driving the field. They are forcing questions that might not otherwise have been asked. And they are, in the long run, going to make our picture of the universe richer, more detailed, and more accurate than it was before. We are lucky to be living in an era when these observations are possible. The tools we have built, from the mathematics of general relativity to the engineering of space telescopes operating at temperatures near absolute zero, represent thousands of years of accumulated human intellectual effort. The questions we are now able to ask about the universe's earliest chapters would have been considered purely philosophical speculation just a century ago. They are now empirical questions, addressable with data, testable against models, and, progressively more precisely, answerable as our instruments and our theories improve together. That is a remarkable thing, and the impossible early galaxies, sitting at the edge of the observable universe, calling into question some of our best predictions about how the cosmos assembled itself, are a perfect embodiment of what makes science perpetually fascinating. The answers are out there. We are building the tools to find them, and the universe, as it always has, will turn out to be more intricate and more surprising than we imagined. If questions like these keep you curious about the universe, consider sharing this content with someone else who would appreciate it. The more people who understand and care about these discoveries, the better the conversation around them becomes, and the better the science that follows. The early galaxy problem is not solved yet, but it is being worked on every day by some of the most capable and dedicated scientists on Earth. And when the solution comes, it will be worth the wait. There is one more thread worth pulling in this story, and it concerns what the impossible early galaxies might tell us about the nature of dark matter itself. We have mentioned dark matter many times in this discussion, always treating it as a well-understood component of the cosmological model, and in many ways it is. We know how much of it there is, roughly 5 times more dark matter than ordinary matter by mass. We know how it is distributed on large scales, tracing the cosmic web in a way that matches the observed distribution of galaxies. We know that it interacts gravitationally and does not emit, absorb, or scatter light. And we know that without it, the observed structure of the universe cannot be explained. What we do not know is what dark matter is made of. At the level of particle physics, The leading candidate for decades was a class of hypothetical particles called weakly interacting massive particles, or WIMPs. These are particles with masses in the range of tens to hundreds of times the proton mass, interacting via the weak nuclear force. Their predicted properties would explain the observed abundance of dark matter as a natural relic of the early universe's thermodynamic evolution, a coincidence that physicists found compelling. But WIMP dark matter searches, using underground detectors, particle colliders, and astrophysical observations, have not found WIMPs. The parameter space where they were most expected to live has been largely excluded. This does not mean dark matter does not exist, the evidence for it is overwhelming, but it does mean that the simplest and most theoretically motivated candidate appears not to be correct, or at least not to be the whole story. Alternative dark matter candidates are numerous. Axions, extremely light pseudoscalar particles originally proposed to solve a problem in the theory of strong nuclear interactions, are among the most well-motivated. Sterile neutrinos, hypothetical cousins of the ordinary neutrinos with different interaction properties, are another candidate. And there are more exotic possibilities, including primordial black holes formed in the very early universe before the first stars existed. The early galaxy problem is relevant here because different dark matter candidates predict somewhat different behaviors for small-scale structure formation. The standard cold dark matter model, in which dark matter particles have very low velocities and no significant self-interactions, makes specific predictions for the properties of small halos and the clustering of matter on small scales. These predictions have been tested extensively and are broadly successful, but there are some persistent small-scale tensions. Warm dark matter, in which the particles have somewhat higher thermal velocities, predicts a suppression of structure formation below a characteristic scale. This would reduce the number of small halos and change the density profiles of dark matter halos in ways that might alleviate some tensions. However, it would also reduce the abundance of the small building blocks that merge to form larger halos, potentially making the early galaxy formation problem worse. Self-interacting dark matter, in which dark matter particles interact with each other through some kind of dark force, can change the density profiles of halos and the rate at which halos exchange energy during mergers. Some versions of self-interacting dark matter have been proposed to address small-scale structure problems while remaining consistent with large-scale constraints. Fuzzy dark matter, in which the dark matter particle is an extremely light boson with a mass so small that its quantum mechanical wave properties are relevant on astrophysical scales, predicts a minimum halo mass below which halos cannot form. This could suppress the formation of very small halos while leaving larger scale structure intact. How do these different dark matter models affect the early galaxy problem? The connection is indirect but potentially important. If dark matter clusters differently than the standard cold dark matter model predicts on the scales of galaxy formation halos, this changes the rate at which those halos assemble and the density profiles within them. Different density profiles affect how efficiently gas can cool and collapse to form stars, and different small-scale structure can change the merger history of halos, affecting how galaxies grow. Whether any of these modifications are large enough to explain the discrepancy between the observed early galaxy population and standard model predictions remains an open question. Most analyses suggest that the modifications are too small, and that the early galaxy problem is primarily a baryonic physics problem, meaning a problem with how stars, gas, and black holes behave within halos rather than a problem with the dark matter itself. But this conclusion depends on the specific observations and the specific dark matter models being compared. As the observations become more precise and the dark matter model comparisons more systematic, this conclusion may be refined or revised. There is also the possibility that the early galaxy problem is connected to physics beyond the standard model of particle physics in a more direct way. Some models of inflation produce not just a nearly scale invariant spectrum of density fluctuations, but also a population of primordial black holes. If those primordial black holes are sufficiently massive, they could serve as the seeds for the rapid growth of supermassive black holes in the early universe, potentially solving the early black hole seeding problem. If primordial black holes also make up a fraction of the dark matter, they could affect the clustering of matter on small scales in ways that differ from particle dark matter. The constraints on the mass and abundance of primordial black holes come from a variety of observations, including the observed gamma-ray background, the results of microlensing surveys, the cosmic microwave background, and gravitational wave observations. Within the allowed parameter space, primordial black holes could plausibly contribute to the early galaxy problem in interesting ways. The detection of gravitational waves from merging black holes by the LIGO and Virgo detectors has provided new constraints on primordial black holes. If a significant fraction of dark matter were made of primordial black holes, with masses in the tens of solar masses range, this would produce a detectable population of black hole mergers at rates that may be in tension with the observed event rate. Current gravitational wave data constrain, but do not rule out a primordial black hole contribution to dark matter at the level of a few percent. The Laser Interferometer Space Antenna, the future space-based gravitational wave observatory planned for the 2030 era, will be sensitive to gravitational waves from merging supermassive black holes at cosmological distances. This will provide information about the black hole merger history across cosmic time and will help to determine whether the rapid early growth of supermassive black holes is consistent with standard accretion models or requires more exotic explanations like primordial black hole seeding. All of these considerations, dark matter physics, inflation, primordial black holes, gravitational waves, point toward a future of science in which the early galaxy problem is not an isolated puzzle, but a convergence point for multiple deep questions. The answer to why early galaxies are so massive and so evolved will likely have ramifications across astrophysics and possibly into fundamental physics. This is the character of the most important scientific problems. They are not isolated curiosities, but windows into underlying principles that connect many different phenomena. The impossibly early galaxies are such a window, and looking through it, we see not just a puzzle about galaxy formation, but a landscape of open questions about dark matter, inflation, black hole physics, and the fundamental laws that govern the universe's evolution from its very beginning. We are fortunate that the James Webb Space Telescope is open and operational, that it will continue observing for many more years, and that the scientific community studying its results is large, talented, and deeply motivated to understand what it is finding. The universe is very patient. It has been there for 13.8 billion years and will be there for trillions more. The answers we seek have been waiting just as long, encoded in the light from the first galaxies, traveling toward us across the immensity of space and time. We are, at last, sensitive enough to receive that light. And now the work of understanding it has truly begun. If you are curious about these discoveries and want to keep following the science as it develops, subscribing to updates from science communicators and following the publications from the Web science teams is one of the best ways to stay informed. The results are coming steadily, and each new dataset adds to our understanding in ways that are genuinely surprising. The universe, it turns out, began with a burst of activity that none of our models fully anticipated. The first galaxies grew up faster than we thought, lived more intensely than we expected, and left behind a record of their existence in light that has been crossing the universe ever since. We are reading that record now, for the first time, with instruments powerful enough to do it justice. What we read there is still being deciphered, but already it is more interesting than we dared to imagine. The story of how we came to understand the early universe is itself a story worth telling in full. Before the invention of modern telescopes, before spectroscopy and photographic plates and radio receivers and space observatories, humanity's entire knowledge of the cosmos came from naked eye observations of the night sky. The stars seemed fixed and eternal. The Milky Way was a mysterious band of faint light. The concept of a galaxy beyond our own was simply not imaginable. The change came rapidly, by historical standards. In less than a century, from the early 1900s to today, our picture of the universe expanded from a modest collection of nearby stars to a vast cosmos of hundreds of billions of galaxies spread across tens of billions of light years, all evolving over a history of nearly 14 billion years from a hot, dense beginning. Within that transformation, a key moment was the realization in the 1920s that the universe is not static but expanding. If you trace the expansion backward in time, you arrive at a moment when everything was compressed into an unimaginably hot and dense state. This is the Big Bang, not really an explosion in space, but an expansion of space itself, carrying all matter and energy with it. The term Big Bang was originally coined dismissively by the astronomer Fred Hoyle, who preferred a rival model called the steady-state theory, in which the universe had no beginning and matter was continuously created to maintain a constant density as the universe expanded. Hoyle intended the phrase to highlight what he saw as the absurdity of the idea, but the name stuck, and the evidence for the theory accumulated overwhelmingly over the following decades. The discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson, essentially by accident while they were calibrating a radio antenna for satellite communications, provided what many consider the decisive confirmation. The CMB is exactly what the Big Bang model predicts. A remnant thermal glow from the hot early universe, now cooled to just 2.7 degrees above absolute zero, filling the sky uniformly in all directions. Subsequent measurements of the CMB, first by the COBE satellite in the early 1990s, then by WMAP in the 2000s, and most recently by the Planck satellite, have mapped this background with extraordinary precision, revealing the tiny temperature fluctuations that seeded all cosmic structure. These measurements have not just confirmed the Big Bang model, but have determined its parameters with exquisite accuracy. The age of the universe, the proportions of ordinary matter, dark matter, and dark energy, the amplitude and shape of the primordial fluctuation spectrum. All of these fundamental numbers are known from CMB measurements, combined with complementary observations of galaxy clustering, supernovae, and other cosmological probes. The consistency between these different measurements, using different physical processes and independent observational techniques, is a powerful argument that our cosmological model is essentially correct. Within this well-tested framework, the story of galaxy formation proceeds. The primordial fluctuations grew under gravity. Dark matter halos formed and merged. Gas cooled and fell in. Stars formed and exploded. And over billions of years, the universe assembled itself into the structure we observe today. This story is broad agreement, with observations across many cosmic epochs, from the early universe probed by the CMB to the nearby universe probed by galaxy surveys. The early galaxy problem is a wrinkle in this story, not a hole. It says that somewhere in the complicated middle, in the transition from initial conditions to fully formed galaxies in the first billion years, our models are missing or mischaracterizing something. The something might be in the physics of star formation, or black hole growth, or feedback, or the initial mass function of stars. It is probably not in the basic cosmological framework. Identifying exactly what is missing will take time and data and creativity. But the scientific infrastructure to do this work is in place. The instruments are operating, the simulations are running, the theorists are thinking, the observers are observing, and in the background, the universe continues its patient expansion, carrying the light of those early impossible galaxies steadily toward us, photon by photon, across the immensity of cosmic time, waiting for us to finally understand what it is trying to say. That moment of understanding is not here yet, but we are closer than we have ever been.